Welcome everyone to a very quick session on environmental chemistry. Let me give you a feel of what is contained in these sessions. In this very first session, we'll be talking about the hydrological cycle, or which is also better known as the water cycle. Here we'll also be discussing about the solvent properties of water and why water is known as a universal solvent. In this second session, we'll be talking about water contamination and the conventional treatment protocol we have, which involves processes like coagulation, flocculation, sedimentation, and filtration. Okay. In the third session, we'll be talking about different water parameters like the dissolved oxygen, the biochemical oxygen demand, the chemical oxygen demand. Okay. These parameters are usually checked after water is treated in wastewater treatment plants. Okay. And also sometimes to check the quality of water in polluted water bodies. Okay. In the fourth and the final session, we'll be also discussing two very important water parameters that are pH and the redox potential. Okay. And if time permits, we'll be discussing them at length. Fine. Okay. So to begin with, we'll start with the hydrological cycle today. Okay. And let's try to understand what the hydrological cycle is and how it is so important to us. Okay. So the hydrological cycle or the water cycle is basically a never-ending process of circulation of water from the clouds, okay, to the lands, and from the lands to the ocean, and from the ocean again back to the clouds. This never-ending circulation of water, okay, is known as the water cycle. Fine. How does the water cycle occur? It occurs in 4 different stages. First off, we have the heat of the sun providing energy. It heats up the ocean water, okay, starts to evaporate. So whatever water vapor is there, it starts to rise slowly because the hot air starts to take it up into the sky. Once it reaches this point, okay, at a very high altitude, okay, this water vapor slowly starts to condense, okay, okay. Here, the initial formation of the clouds take place, and then they start clashing against each other, colliding against each other, okay, and then they become bigger and bigger and bigger, and then it forms clouds. So first off, the process is evaporation, or sometimes from the plants we also have another process, giving off water, okay, that is known as transpiration. Okay, we can take both these processes into account. So after evaporation, as it reaches to a certain height, it starts to cool down and condense. Okay, that process we call it condensation. Okay, now the clouds start to move around, okay, with air, with the wind, okay, and go to different parts of the world. When these clouds become heavy after clashing against each other, okay, when they collide against each other, when they become heavy, they start to fall down. They start to fall off the sky, and we call this precipitation. We call this precipitation. This is the third stage. Okay. The precipitation can happen in the form of rain or in the form of snow, okay, depending upon the temperature. So once this precipitation occurs, it comes to the land, right? And from the land, it might run off, it might percolate deep into the earth, it might go off as runoff. We call this runoff or percolation. And this is the final stage, after which the water again comes back to the ocean. So this continuous never-ending process is known as the water cycle or the hydrological cycle. Okay, so how is this hydrological cycle important? This is important for the very existence of something we call the hydrosphere. S-P-H-E-R-E. Now you might be wondering what this hydrosphere is. Okay, this hydrosphere is nothing but the combined mass of whatever liquid or frozen water that's present in Earth. Okay, meaning the components of the hydrosphere are the ocean, it can be, the ice caps, it can be, there might be glacial deposits here, it could be all the water that has percolated, seeped down inside the earth, okay, and which remains in a water table. That could be groundwater, it could be surface water in the form of lakes, rivers, sea, whatever it is, okay. So all this combined mass, which constitutes at of around 75% of the total earth, okay, that is known as the hydrosphere. Okay, so, and why is this hydrosphere important? It is important because 75% of any cell in a living organism is constituted of water. Okay, so if that is the case, you might as well try to understand how important it is. Okay, if hydrosphere is not there, we don't exist. Okay, number one. Number two, this hydrosphere itself is a very vital habitat for every living organism on Earth. Okay, it can be aquatic life, it can be life on the surface of the earth. Okay, whatever it is, the hydrosphere is very, very important. The third and another important aspect of the importance of hydrosphere is that it controls, it regulates. This would be a better word to use. It regulates the temperature on Earth. Okay, it regulates the temperature on Earth. That's why it becomes very conducive for living organisms to live on Earth. Okay, so that is how the hydrosphere is important. Now, why is the hydrological cycle important? Now, since hydrosphere or water is so important for living organisms, okay, if the cycle wasn't there, okay, if the cycle, this perennial, continuous cycle wasn't there, the hydrosphere that's present on the earth would be continuously getting depleted. Okay, if we didn't have any, source of water coming back onto the earth or into the oceans, then this would be continuously getting depleted, so we wouldn't have the constant supply of water for us. Okay, so that is why the hydrological cycle is very, very important. Okay, the hydrosphere is only one of the subsystems of the earth. The planet earth has 4 subsystems. Hydrosphere or water is one. Okay, the land, this land, okay, or lithosphere, it's also called lithosphere, is the other subsystem. The atmosphere or air is the third subsystem, a sphere present on the earth. And the fourth and very important is us, that is the plants, okay, we human beings, animals, whatever living organisms are there, this is the first subsystem, that is the biosphere. Okay, so the hydrosphere interacts with the atmosphere, the biosphere, the lithosphere, okay, all these different spheres, subsystems of the planet Earth, and that is why it is very, very important. It gives us, it is the source of water for us, for living organisms. Okay, so if hydrosphere is there, we exist. So that means if water is there, we exist. Why do you think water is so important to us? Why do you think water is so vital for, life on Earth? Because most of the planets, okay, we know, don't, as far as we've known till date, don't have life forms. Okay, it's only planet Earth which has life forms on it. Now this is because of the presence of water. Okay, so water is very, very vital to us. The reasons being, as I've already said, 75% of the cell in our bodies, in any living organism, is constituted of water. I'll read the molecular formula for it. Okay, number one. Number two, most of the minerals or compounds or elements or whatever you might chemically want to write it as, are easily soluble in water. So as they can easily dissolve in water, okay, this can reach different parts of our system very easily. The third, aquatic life also needs minerals, but in addition to that, they also need oxygen or carbon dioxide, whatever it is, for their survival. And these dissolve in water. Water is a carrier for them. Okay, so if you look at it in a gist, what does that mean? The very existence of life, we need water. So that's what is very, very important. So we need to understand, next on, we need to understand why these, for the existence of this life or not, why do we really need water? Okay, and the point I have specified here is very important. Most of the minerals and elements are easily soluble in water. Okay, this means that water acts as a very good solvent. Okay, it acts as a very good solvent, meaning it can dissolve most of the minerals, the ions, whatever it is. Okay, maybe molecules, gases like oxygen, carbon dioxide, whatever it is, it dissolves most of it, and then it takes it to different parts of our physiological system. Okay, so that's why it is very, very vital. Okay, now why is water a very good solvent? Now you need to understand this from the chemistry viewpoint. Okay, only then it becomes easier for you to understand why water acts as a very good solvent. Okay, from the chemistry standpoint, we look at water as a compound made up of one oxygen atom and two hydrogen atoms. That's the molecular formula for water. Okay, the structure is something like this. Okay, the oxygen atom and the hydrogen atoms are connected via something called the covalent bond. I have to go into this detail because this will make it easier for us to understand why water is, shows certain properties. Okay. When we have this covalent bond and the electrons are being shared between the two, we have again another effect that comes into play. Oxygen is an electronegative atom. Okay. Hydrogen is not so electronegative. We can take it to be an electropositive atom. Okay. So what happens is the electrons gets pulled more towards oxygen rather than hydrogen. Okay, because oxygen being an electronegative atom. Now you might be wondering as to how oxygen becomes electronegative and why hydrogen is not electronegative. Electronegativity is something of an intrinsic property that's inherent in the atom or the element. Okay, because of its configuration. Okay, now you might be wondering again what configuration is. Okay, fine, I'll give you an example for this. Okay, let's take the case of a hub, say a city center. Okay, the city center houses different showrooms of different brands, right? Like you have the Pantaloons, you have the Soccer Stuff, we have Miniso, we have Adidas, Puma, whatnot. Okay, so we have different brands, showrooms there. We have different eateries there, the KFC, the Starbucks coffee, right? So there are many shops there. Okay, what is the configuration of the city center? So the configuration of the city center are those shops there. Okay, that's the configuration of the city center, right? Okay, what does the configuration of that city center do? It attracts people. It attracts customers. Correct? Similarly, we have different kinds of atoms with different kinds of configurations. City center has one kind of configuration. Okay, there might be another mall or plaza, whatever it is, with a different kind of a configuration. So these different configurations allow these kinds of centers to attract people. Okay, some attract people heavily, some less. Similarly, oxygen has a different configuration. It is made up of electrons and atoms placed in a different way than hydrogen. So its configuration is different, its configuration is different. Okay, so that allows this, okay, sometimes gives it the capacity or the tendency to attract electrons more than them. Okay, so that means when these kinds of atoms get this inherent tendency or capacity to attract electrons more towards itself, we call these kinds of atoms as electronegative atoms. Atoms which do not have that kind of tendency, okay, or which has the opposite tendency, it has a tendency of giving off electrons, then we call those atoms or elements as electropositive. Okay, so that's how you relate configuration with electronegativity. Correct? Okay, fine. So when this happens, what we have with us is the electrons getting pulled towards oxygen. So there is an electron density which is in excess and electron density which is deficient on these atoms. Okay, so in chemistry we tend to usually designate them as del plus and del minus, atoms having del plus and del minuses. Okay, so what we are trying to do is we are trying to show that this part of the molecule is deficient of electrons, while this part of the molecule has an excess of electron density on it. Okay, so when this happens in any molecule, we say the molecule is polarized, or we call the molecules as polar molecules. Okay, so water is a very polar molecule. Okay, this is very important. Now, since water is a very polar molecule, we have something called like dissolves like. So water being a polar molecule, it will attract or dissolve, okay, other polar molecules or ionic molecules or compounds. Okay, so when this happens, when it has this capacity to dissolve polar molecules and anionic compounds, okay, there are lots of polar molecules and anionic compounds in nature. So since water is a polar molecule itself, it has this capacity to dissolve polar molecules and ionic molecules. That is why water is called as the universal solvent. But the other thing that you need to also understand is, being polar, how is it able to dissolve these molecules? We'll just take a simple example again of the molecule or compound that we just discussed, sodium chloride or the table salt. Okay, when you put sodium chloride in water, right? When you put sodium chloride in water, we find that after a little help with stirring, we find that it gets dissolved. We don't see any more of the crystals of sodium chloride in water. It gets dissolved. How does this happen? Okay, now we go back. When sodium chloride gets into water, okay, sodium chloride, and we have lots of water molecules there, okay. The water molecules start to surround the sodium chloride compound, okay, molecule, whatever it is. And when the sodium sees, because sodium is a positive ion, because it is electropositive, when it sees that these water molecules are surrounding it, okay, and it sees that positive charged H plus are near it, or negative charge O minus is near it, it tries to form associations. The sodium, because it is electropositive, will try to form association with negative O minus ion, O minus polar oxygen atoms. Okay. Chloride, on the other hand, is electronegative. Okay. So when you have del plus hydrogen, del plus atoms near it, it starts to form associations with them. Okay. So what happens when it starts to have associations with the other water molecules, okay, via weaker interactions, it starts to, the bond between sodium chloride starts to weaken, and finally it breaks. And this we call a process called as dissociation. So we say the sodium chloride dissociates into Na plus. We remove this Cl minus. So Na plus is now, stabilized by interactions with, let's not put it like this, interactions with O minus, okay, and Cl minus is stabilized with interactions with H plus. So when this happens, we say that the sodium chloride has dissolved in water. So water, being a polar solvent, is able to solubilize or dissolve polar compounds and almost all ionic compounds, most ionic compounds. Okay, so that is why it is known as the universal solvent. You also need to understand, despite the fact that it can dissolve most of it, there are still molecules and compounds which they are not able to dissolve, like non-polar molecules. There are molecules which are non-polar in nature, which are not polar in nature, non-ionic molecules. Okay, these molecules, some hydroxides, okay, let's not put it like this, some hydroxides, these are insoluble in water. Okay, then despite the fact that it's not all these kinds of compounds are not soluble in water, why do you call it as a universal solvent? We call water as a universal solvent because it can dissolve most of the substances that are present in nature. No other solvent has this capacity to dissolve, most of the compounds.